Right, so today what we are going to do is start a new topic, and our topic is material selection in mechanical design. This topic will continue both in this week and the next week. Because of the PD day, a lot of the labs, like on the ones on Thursday, will not take place. So essentially, the lab for this topic will start from Sunday. So those who have a session with me on Sunday, I'll start with them on Sunday, and then the other sessions can continue. And then we will also have some more lectures related to this in the next week as well. This topic is important from the point of view of your project as well, because part of the project asks you to carry out material selection for the drive shaft that you are going to design. So that's why I thought it will be good if I can also record these sessions for those students who are unfortunately away. Some of them may be because of the CAPCO, others may be because of road blockage or whatever reason. So we'll go through the material selection and material mechanical design, and if you want to read more on this, we have a supplementary textbook for this topic. This book is not same as the main book, so please make a note of this. So this is Material Selection in Mechanical Design by Michael F. Ashby. And I am using 4th edition because this edition is available freely to the students from the library through the Novel app. Okay, so there is an app called as Novel, Knovel, and you can, as long as you are on the university network, you can access that through the library subscription.
If I use my student account, I can view it? Or
you'll need to check that from library. I think you can still view Novel from your home as long as you are connected through the university account, but I cannot confirm that. Library will need to confirm that. So chapter 4, 7 and 8 are the ones that are most relevant. We'll start with chapter 4's discussion today, and hopefully in the lab sessions we'll go towards more advanced topics. So this is some of this is something that we have already covered in strength of materials. So those students who took the strength of materials with me, we may find some of it as a revision of what they did in strength of materials, but this is deliberate because I don't want to jump into the deep end without again covering the initial concepts related to this. So that's why I've paced the lecture in such a way that we'll start from the start and take it to more advanced concepts later. So the learning outcomes therefore for this session will be to understand and apply the formal material selection process, and mainly at embodiment level, and you should be able to master the following steps. That is translation, that is how you convert a given situation or design requirement into objectives and constraints. Once you have done that translation, then how do you identify and calculate constraints, then how you define the objectives and then rank using those objectives, and how can you combine constraints and objectives to form multiple material selection indices. And then in the lab session, we'll focus more on using the software Granta EduPack, which I also call as CES because of its old name, Cambridge Engineering Selector. So to select appropriate materials for the different cases, and in particular for your drive shaft example as well. So there will be additional slides uploaded on D2L as well that will allow you to work with CES independently. So there will be a lot of videos there. Some videos are directly the ones that I have made for your particular sessions, but then I have also copied links to some other external videos produced by Granta as well. So you have enough resources to keep working on the project then. Okay, now the design, when we are going to talk about the material selection, so we look at the design process of any engineering component as interaction of the following items. So we start by looking into the function of the object. So this function we characterize not at a whole machine level for the point of view of material selection. So obviously, for example, if I talk to you that you are going to design an aircraft, then you are thinking about the whole aircraft's function, which is to carry passengers from A to B, right? But from the point of view of mechanical design, at component level, it's not about the whole machine. It's about the individual components within the machine. So for example, within your aircraft, your you have separate components, like the wings are performing certain separate function as opposed to fuselage. Then within the wings, there are separate components. You can even go further down in that depth. So you can think about the wing being composed of outer skin and then inner ribs as well as spar structures. So each one of them from a mechanical point of view perform a different function. So we are looking here at the component level function to begin with. Okay, of course this can then be linked with the overall function of the machine, but because the material selection has to be carried out at component level, because each component within the machine can be made out of a different material. And it's very common to have that, you know, within the same machine you can have some parts made out of rubber while others made out of steel. So that's a very common thing. And why that happens is because the different components of the machine have different functional requirements and therefore they have different materials. Okay. So in this case, when we are now talking about that function, we can basically isolate that function in terms of basic mechanical functions if we are looking at it from a mechanical point of view, such as, is the component supporting an axial load? Is the component supporting a bending or a beam type load? Is the component under torsion? So then it's like a shaft, right? So those type of basic functions that we are talking about. Now each of those functions get performed best using a particular shape. So that's why now, for example, a beam can have a rectangular cross section, but it can have a I-beam cross section as well, right? Similarly, a shaft can have a circular solid cross section or it can have a hollow cross section. So the shape is directly linked with those performance functions. Okay. Now, both of these aspects, when you look at them together, will give you certain material properties that can then help you identify the appropriate material for it. But this selection of material is complicated by the fact that not all materials can be processed using the same type of manufacturing routes. And therefore, whatever is your capability in terms of processing, in terms of both actually having the machines or having the cost effect, you know, of that processing method, and or for example the volume effect of that processing method, because some processes are more suitable for small scale production, other are more suitable for large scale production. So you may have additional constraints on your material selection because of the choice of the process that you have. Okay, and this is linked with both the material as well as the shape that you can produce. So that's why I have shown all of these arrows being linked together to define your material selection. Furthermore, as now, you know, the environmental concerns are becoming more and more important for us as an engineer to deal with, because we understand the implications of the choices that we make in terms of material selection, that how much they can affect the planet. We need to think about the environmental effect of the material selection in parallel to the other aspects. So these may not be input as a direct constraint on material selection, but often once you have, you know, achieved the basic performance requirement, basic shape and the process, then you compare different options in terms of their environmental impact. Now this environmental impact can be in terms of the processing energy required, or it can be in terms of the CO2 being emitted, or it can be in terms of, for example, requirement of water usage, okay, for a particular product, or it can be in terms of the potential to recycle the component at the end of its life. Okay, so all of those environmental impacts can also be considered at the same time. But what a good engineer never forgets is the cost implication. So all of this has to be done at a competitive cost. Otherwise, no matter how much perfect or best material you have selected, you are not going to be in business. So this all has to be done at a competitive cost. So this defines the overall framework in which we will look at material selection for mechanical component design. Okay, let's now look into the different phases of the material selection, because each phase, the depth at which you can go and the freedom that you have to select material is different. So I defined these phases in the very first lecture. So if you remember, we defined the conceptual design phase, we defined the embodiment level phase, we defined the detailed level design phase, and then we said after that we move on to the prototyping before we can actually go for mass production of the item. So these are essentially the 4 main phases of the design before you go into full or serial production. Now, in most of the material selection is most effective if it is carried out at embodiment level. Now, why I'm saying that it is most effective at embodiment level? Because when you are at detailed level, almost everything is fixed. Your geometry is fixed, the form factor is fixed, you'd have very little control on how the component is going to interact with other components. So, for example, you cannot change its diameter or you cannot change its other properties that are going to change the stresses within the component, right? So, at detail level, yes, you can carry out a material selection, but that will be for a very narrow class of materials that will all meet that specific requirement. But when you are at embodiment level, you have a number of variables that we can call as free variables. So, for example, you can think about this from the point of view of a simple component like a axial rod. Okay, that axial rod, when you apply a tensile load to it, by simply changing the diameter, you can alter the stresses. The same axial rod, if you make it out of a bigger diameter, you can use a material that has a much lower yield strength, isn't it? So at embodiment level, you are still playing with those parameters, right? Of course, you will have certain upper and lower limits for the diameter, but you are still able to modify a lot of geometry as well as how the loads are being applied. So all of those things can be modified. Therefore, the maximum cost benefit that you get, or the maximum, for example, the weight saving that you can get from your design is if you do the embodiment level material selection first, then move on to the detailed material selection, and then at detail level, then you make sure that whatever you selected at embodiment level, you are actually able to use it at that level. So in this course, that's why I will emphasize more on the embodiment level material selection, and therefore things there will always be an element of openness in terms of our choices. So maybe after the end of the selection process, you will still end up with more than 5 or 10 different options. Why? Because you still have a lot of flexibility in terms of your design, right? So that's what we will do, and then we can take it to the detail level. Okay, now moving on to the next aspect of how this process actually should take place. Now, obviously, different authors and different researchers have given different schemes. But most of them have these common elements that I will be talking about. They may be referring to them in different ways, but essentially the central idea is same. Okay. Now, the scheme that I am here trying to discuss, it's mainly based on Professor Ashby's work in this area, and that's why I'm using his book here as well. So that basically divides the selection process into 4 distinct steps. The first step is that of translation, meaning you look into your machine first of all, then you look into the individual machine component, and you look into the function of that component. So for example, right now in the class you have this projector in front of you. So let's say we are talking about the support of the projector with the beam, right? The beam that is there. So when you look into this from the point of a functional requirement, the function of the beam is to support a bending load, right? So that's now defining the function in mechanical terms, right? Now, once we have looked into that function, we then start thinking about, okay, what are the constraints? Now, obviously, you are not going to design this beam that is supporting the projector for, a massive load like 1 ton, because you're not going to hang a 1 ton load from it, right? So you are going to look into the typical weight of the projector that you are going to use to hang it, and then have a certain factor of safety and then account for other effects, like maybe somebody while he's mounting it, there is a shock, there is a impact type of load, right? So looking into those factors, you'll choose a reasonable load that is going to be applied. And from that you start thinking about the constraints, because that load will result into certain material properties that will be required, like the strength, for example, the flexural strength. If the component on the other hand is being used for, let's say, an application where cyclic loading is expected, then you may be looking at fatigue strength. Similarly, how much deflection is actually allowed, because obviously once this projector is installed, you don't want to keep this moving up and down. So right now it's being mounted as a cantilever, and cantilevers can move up and down very, very easily. But if this projector starts moving down even a few millimeters up and down, your whole view for the audience will get ruined, right? So you want it reasonably stable with only maybe very little deflection possible. And that will then lead to your other constraints on other properties, such as Young's modulus, for example. So the translation is basically taking that problem from an everyday person's language and converting that into an engineer's language, where he identifies the function in mechanical terms, where he identifies the constraints in mechanical terms, and where he then defines the objective of the material selection, because each thing having a different use can have a different objective. In this case, it's an everyday item. So most likely the objective will be to keep the cost as low as possible, while in other applications there can be other objectives. And then you also at this stage decides that, okay, what are the other free variables? Because you see, for example, the length may be fixed because based on what the projection distance has to be, but then can you change the width of the beam? Can you change the thickness of the beam? So those may be your free variables. So you decide those things in the translation and come up with a clear definition of all of them. Once you have completed your translation phase, you move on to the actual screening phase. So screening phase is where you start by applying your constraints. So now this is where you are going to input the properties such as, okay, this is the maximum yield strength I need. This is the maximum this is the minimum acceptable Young modulus that I need. This is the minimum acceptable strength that I need. This is the maximum density that I need. So you start applying those constraints. And that all depends on your translation, that what those constraints will be. But to apply those constraints, of course, you need some sort of a database, because obviously if you know where the material properties or what are the possible candidates, only then you can start applying those constraints. So you basically screen out the obviously wrong choices first, and then you are left with a smaller subset of materials. Once you have that smaller subset of materials, then you start the ranking process based on your objective. So like I said, in this case, the objective may be to reduce the cost, right? So in that case, let's say you had 100 materials and after the screening, so now you are going to rank them by the lowest cost possible, okay? And then you are going to make your materials final selection and recommendation. But before you make your final recommendation and selection, the very important last step is to consider documentation. Because you see, mathematically, there may be options that seem very, very promising to you. But when you go, there may be other practical constraints. So for example, there may be some trade embargoes in place. So you may want to use carbon fiber, but maybe you are not allowed to import that grade of carbon fiber that you are suggesting, right? There may be some health and safety concerns. There may be some societal concern. Maybe something is made out of pork fat. And now in a Muslim country, that may not be acceptable to be used, right? So you have to look into it from the point of view of past use cases, from the point of view of ethical as well as societal concerns, okay? And then you basically make your final recommendations. So this 4-step process is what we try to follow in all material selection. Okay, let's try to, although I have already explained the process using one example, let's try to look into this now with another example. So right now the example that I have given you is that of this bicycle. Now this bicycle that you have over here, Within the bicycle, you can be talking about different components, right? You can talk about the bicycle as a whole, but you can also talk about different components within the bicycle. And each component, as like I was saying, you see, when you do the translation, you have to do it at component level. Because yes, the bicycle has an overall function, but the tires have a different function. The frame has a different function. The handlebar has a different function. The chain has a different function. And therefore, each one of those subcomponents will require a different material, right? And therefore, the translation will be different for them. So right now, I can pick any of the component. And the first step that I am doing is I'm saying you define the function and you express your design requirements as constraints and objectives. So anyone in the class, let's say I am talking about this column which is supporting the seat, and I'm trying to do a material selection for that. Okay, so simple component, a column on the top which is supporting this seat, and how will you express the function of this? What is the function? In a mechanical engineering term.
Resisting load.
Yeah, but what type of load? You have to be more specific. Because you see, when you apply load as a beam is different than when you apply it as an axial. Okay, axial. But is it primarily axial compression or tension? Compression, right? And that makes all the difference. Because when you are in axial tension, your primary concern is to avoid failure because of yielding or ultimate strength being exceeded. But if you are in compression, your primary concern becomes buckling, isn't it? And we studied that earlier in the course. And that means there are different design variables that will be important for you. Okay? Of course, it has to still withstand the load so that it does not yield plastically, which means that one of the design constraint will be based on yield strength, but at the same time, you have to make sure that it does not buckle. And that means that the other constraint will be based on Young's modulus, because remember the Euler buckling equation? It had the Young modulus in it, right? So that starts, so you see, that's why I'm saying it's important to define the function specifically in terms of the typical words that we use in the engineering. So right now, from an engineering point of view, this rod is actually a column under compression. When you describe it like that, immediately in your mind, those variables should now start clicking. That it has to have certain yield strength, the Young modulus is important, okay, and that's the primary function that it is doing. The profile itself can be different, and we can talk about that later. But now let's talk about the objective. So these were some of the constraints that will be there on this column, right? But what are the objectives of this kind of a design? So I'm saying we have already now defined some of the properties that will act as a constraint, right? So right now we looked into constraint in terms of the material properties. There can be other constraints as well. For example, what will be the overall length, right? That has to be fixed based on whether the bike is being used for an adult or for a child, right? So those constraints will also be there. So there will be some geometry constraints and some material constraints. Now I'm saying is that in terms of the objective for the material selection, so what is objective? Objective is like a goal, right? It's not a fixed number. It's not something that you must have a yield strength of this or you must have a minimum Young modulus of this. It's like a goal. The more it is, the better, or the less it is, the better, right? So in this case, what should be an appropriate objective for your material selection? So that is already being taken care of from your constraints. So yes, it has to be strong, but we are not saying it has to be as strong as possible, because then you'll make it, out of, I don't know, for that particular so that's why when we say strong enough, then that means it's like a constraint. You are putting a fixed number there. That after that, everything else is same, right? Because obviously this bicycle is going to be used by maximum, If it's for a child, maybe you'll design it for maximum 60, 70 kgs. If it's for an adult, you can design it maybe for 150 kgs. That's the typical maximum load you'll design it for, right? Then if it is being used for mountain biking, maybe you'll consider the impact load as well. So the actual load will go up, the design load will go up for that case, because it will be taking those jumps, high jumps and things like that. So the actual impact load, effective load will increase, but your initial design load will still be 150. So you'll end up with a fixed constraint on that. I'm saying, what should be the objective of material selection? One of the possible objective that applies to almost all engineering products. It should be made cheapest. But this is debatable now. Okay?
Should be balance between cost and efficiency of the function.
Yes, but then how we define that balance? Because you see, cost itself is a very is something. Yes, we say overall it has to be the cheapest, but what is being defined as cheapest for Rizwan is different for what is being defined for as cheapest for the royal family, right? They have a very different sense of cheapest, right? If this bike was being designed for an Olympian, the meaning of cheapest will be very different for an ordinary customer, right? So I hope I'm trying to make that point clear. So basically that is linked with then the target audience, okay? But yes, cheapest is often a very useful objective. But then there can be other objectives as well. So for example, if this is a ordinary bike for a customer, for general purpose, maybe you don't care too much about how heavy the bike is, right? It will be a consideration, but you'll have like a target weight. But if this bike is being made for an Olympian, then price is a secondary consideration. Making it as light as possible is the primary consideration, because even losing 2 kilos of weight in the overall bike weight can mean a difference between an Olympic gold medal and a silver medal.
It depends on the use.
It depends on the use. So the objective is something that is dependent on the end use of the component, and you have to decide on it as an engineering team, right? Same product for different end use and different customer needs will mean you will have different objectives. So for example, in your motorsport shaft that I gave you as a project, right? The objective for a commuter car can be, it should be as cheap as possible. But if you are talking about a high performance sports car, then it has to withstand the highest torque. Because there you're not going to compromise on cost simply because, because at the end of the day, your performance matters there, right? And weight reduction matters there, right? So your objectives change, right? So if we look into this, then if we look into the constraints and objective, I've given you certain constraints and objective here. So things like ability, the stiffness or the strength are some of the constraints. But then there are other constraints which are not mechanical in nature, but they may be related to the processing ability. You must be able to make it in the form of a rod. If it is only a fiber, for example, you cannot make it in the form of a rod that can withstand compression. You have to put it as a composite then, isn't it, with some other metrics, and then you can use it, and then that changes the properties. So you have to be careful when you're selecting your material, that is that also possible or not to be molded into that shape for that material, right? Let's say, so then similarly, if for many objects, an aesthetic appeal is also very important, yeah? So what kind of surface finish you can achieve with that particular material. So those become your constraints, along with the mechanical constraints like stiffness and strength. And then the objectives are things like being as cheap as possible, being as light as possible. So those are your objectives. So this is basically what we mean by translation, and from that translation identifying the constraints and objectives, okay? Now once you have that translation, you move on to the next phase of screening. Now for the screening, you need data. So data is then the main thing that you need, and for that we then therefore use different softwares. Obviously, if you don't have a software, you'll have to do your own search, you'll have to go to different suppliers, collect the data in your market, and then do a manual sort of a comparison, right? But because of now wide availability of the different software databases, we can at early stages of design compare the different material options based on the general data available in those softwares such as the Granta EduPack or the Ansys Material Selector, right? So that those softwares list properties like density, price, Young's modulus, strength, durability, or process compatibility. So a good software will have a list of all of those attributes. Okay. Now again, Granta is just one of the software packages. There are so many others. Okay. So I'm not specifically marketing for Granta. Please forgive me. It's just that that's the software that we have available in the university, and because that approach has been there for a very, very long time, so it's tried and tested. Okay. So that's then the where you do your screening. So basically, your software then provides you that comparison engine or interface that allows you to screen the obviously wrong options from the options that may be possible. And that's the step of screening. Once you have done the screening, you move on to the next phase of ranking based on your objective, right? So if you are making this bicycle rod for a general children use, then the price will be your objective. And basically out of, let's say, your 50 options, which are all good from the point of view of your meeting your performance targets, then you will select the one that is the cheapest, right? And that's how you are going to rank it. And then a good software will actually also give you a lot of documentation. But for this phase, you may have to carry out external market research as well. And once you have done that, then you will make your final selection. So I hope the overall process of material selection is clear. Any questions on this so far? Yes. Good. Excellent. All right. So let's now move on to an important concept that I will keep on talking about again and again. And it's called as a material index. It's also called as Material Performance Index. And in other places, people may just call it as Performance Index. Okay? So what does it mean? It just means that it is a metric of excellence for your component, meaning that you can use that in combination with your constraints and objectives to define the correct material for that application, right? Normally, this material index, it can either be, a single property, or it can be a combination of properties. Now, for a simple selection, we can maybe use a single property. But for more complicated selection, where we are looking at the combined effect of the constraint and the objective, we often have to define it as a multi-property index. Okay. So how we form this? We form this by linking the component's functionality through equations to its constraints and objectives. So that's the formal way of doing it. Now, let me show you some examples. And again, this is something that we covered also earlier in the strength of material, but I will look into this. So if you look into this particular object in front of you, the component, right? The component has, this bookshelf that you are seeing in front of you has different subcomponents. Each subcomponent is performing a different function. But overall, for this kind of an everyday shelf, probably price is one of the primary concerns, right? Then you can have other limitations on how much total mass has to be, but again, you can express that as a constraint, yeah? But overall, you would want to do it at the lowest possible price per unit volume or per unit mass. Now, the constraints for this kind of a design will be on quantities such as strength. So maybe, you are designing this shelf for a 100 kilogram load or 200 kilogram load. That will depend on where you want to use this shelf. Then you have the constraint based on the stiffness, meaning how much it needs to deflect down. Okay. So those who did the strength of materials, they actually did this as a small assignment project as well, isn't it? Yeah. So you looked into the whole process of going through the design of it. But what you probably did not do is actually looking at each of the member as a separate component and then creating a material index for it. So let me now look into this. So for member 1, which I am pointing over here, the function is to resist axial load without yielding, right? So this member over here is acting like a truss member, okay? So this truss member, for the point of view of cheapest cost, can be expressed with the material index sigma yield divided by density into the cost per unit mass. Okay, so basically we are saying that the material index is that yield strength divided by the cost. Okay, and because that cost is per unit mass, that's why I'm multiplying it with the density. Now you may be thinking, okay, fine, it looks logical, but how did I actually end up with this equation, right? So we will be talking about that more, but let me first show you some more equations to highlight how this can be different for different object. For the member 2, one of the functions will be to resist bending stresses without excessive deflection. So when you look at the member 2 now, the material index will actually change. Why? Because the function has changed. There the function was resisting axial load. Here the function is bending load. And the same material index in this case will now be, in case of the deflection, can be expressed as Young modulus raised to power half divided by density, which is rho, and then Cm is the cost per unit mass, and cost per unit volume will be rho Cm. Okay, so you are now having a different equation because you are looking at it from a different functional perspective. Okay, the objective is still the same, minimizing cost. It's the function that has changed. Now you can also look into the rivets or bolts design, and the bolts design will be to resist direct shear without fracturing or yielding. So now again your material index will change, and this time the material index should be expressed in terms of shear strength of the bolt, not the tensile yield strength of the bolt, right? So this will be also different. You understand the point? So basically, depending on each function is different material index for the same objective. Of course, if you change the objective, then it will also be different, right? But if even for the same objective, the material index is changing depending on function. For the same component, sometimes you have to have multiple functions. So for example, this axial member, I just described one function. But if you look at it from the point of view of compression, it must also resist buckling. And in that case, actually, I can tell you that this top index will again come up. Not because I am copying it from there, but once we do the derivation, you end up with the same equation. Okay, so this top equation will come up for this member as well. So you will have two material indices then, okay, for the same member. So you can have 2, 3, or even 4 material indices if there are multiple functional constraints on there.
But do you account for all of them?
It depends on what is more important to you, right?
Okay.
So as an engineer, you have to make that decision.
So you only take one?
Not necessarily. For simplest design, we can take one, but as soon as we start going into more detail, then we must account for more than one material index. So that's why I will be showing you more complicated cases, and especially for your shaft in the project, I'm expecting you'll at least take 2 material indices, if not 3. Okay.
And if the objective, for example, instead of being the cheapest, it would have been
Cost.
not cost.
Mass, for example.
Yes,
Yeah.
exactly.
Then this material index will change. Okay. In this case, the change is simple. That's only the Cm will drop. But I will cover now in the later part of the session that how you derive this. And even if you cannot derive this, you already have a list of material index for maybe 50 different functions. That's already available as a appendix within Ashby's book, and it's also available to be accessed from the software CES. And I have created a small video tutorial which will come at the end of today's session. So that one will tell you how to look up for the different material indices directly from the software itself. So you don't always have to derive it. As long as you can look at it, look up that particular material index, you understand the function, you understand the constraint, then you look up the right equation, and then you use that. Okay. Now, I'm giving you one more example. Okay, and this one now is minimum weight design with the different indices. So in this case, you have a tensile tie here, right? This tensile tie is basically resisting axial load for a particular and the objective for an aircraft is not to reduce the price, it's to reduce the mass, because that's what makes it fly. And because for a aircraft, initial price is less important as compared to its running price, which depends on the fuel, and the fuel consumption is dependent on the mass, right? So that's why here the objective is to reduce mass, and then the constraint for this tie becomes sigma yield over density. For this strut, it's now compression. Therefore, the index becomes e raised to power half over rho. Similarly, for the main beam spar, this is now a beam, but now controlling the deflection is important. So again, the same index is appearing, e raised to power half by rho. For the undercarriage, it's not just the controlling the deflection, but the strength is also important, right? The compressive strength is important in this case, and therefore the sigma yield raised to power 2 by 3 over rho is the index. Now again, I know you will have question, where is this equation coming from? So very soon we'll be talking at that. So this is now derivation of material index. I hope, if you don't mind, if I carry on, because I want to complete this today, yeah? As long as the other instructor does not walk into the room. Okay. So let's look into this. So let's start with a very simple case of an axial rod. Okay. So this is now like your tie constraint of that aircraft, yeah, or the axial member, which is pulling the which is under tension, basically, which is being pulled. Okay. So the force F is being applied. In this case, you have different variables, like you have a certain mass of this rod. You have certain length, you have certain area, the material will define the density, sigma yield will define the yield strength of the material. Okay. Now, in the initial phase of the design, you may have certain things which are fixed and certain things which are free at embodiment level, right? So at embodiment level, let's say we already know that this is because it is linking these two wings, so it has to be this much distance apart. Right? So now we are saying that so I'm saying that we already know this distance, therefore the length is fixed, right? But we still have an option to have different areas, don't we? Yeah. So we can, of course it has to be reasonable. It can't be like bigger than the wing size. It has to be within reason, but the area is free variable, essentially within a range. Right? So area in this case is free. Now, right now I am considering it to be a solid cylinder. It can also be hollow, but that will complicate things further. So I'm right now only keeping it as a solid cylinder. Okay. So that cable therefore has a free variable. So I've said what we have free variable, because I've already discussed this, so I'm not going to go into too much detail. But basically, this variable is a variable that can be chosen or modified to satisfy the constraint on material selection. So there can be several free variables. So one of the free variables is, of course, the choice of material, because as soon as you change the material, you end up with a different yield strength and a different density, and that basically allows you to then choose material. From the point of view of the geometry, you can have it either hollow or solid. You can have it round or square. So those are your design choices as well, right? So at embodiment level, if we look at it purely from the point of area, we are not right now fixing whether it has to be rectangle or something else, but for the purpose of derivation, we have to consider one particular shape, right? So that's what we can do. So right now, I'm looking at it from the point of view of area and not in terms of radius, because if I look at it from the point of view of radius, then I'm saying that it must be round, right? But what I'm doing is applicable whether it is round or rectangle or square, okay? So that's what I'm going to do. So let's now move on to the next phase and see what are the constraints. So in this case, like I said, length can be one of the constraints. So as a designer, I'm telling you now that length is fixed in this case, okay? The other constraint is coming from the functional requirement, right? So for this aircraft for which this tie is being designed, the designers will know what will be the typical maximum load F that will be required from this wire, okay? So they will have some idea of that. So based on that, we have the load F requirement. Now think of an equation that allows you to link the geometric free variable in this previous case, which was our area, right? So that was our geometric free variable, with a relevant material property that defines the constraint. Stress equation. Come on, guys. Basic force over area, isn't it? So it's linking your constraint force with free variable area, right? So stress, that's, you see, is the basic equation that you can use in here. But now think about it. If this was acting like a beam, this equation will be different. It will be MC over I. And that's why the final form of the constraint of the material index will change, right? But right now, the equation is simple. It's force over area should be less than the sigma yield. Okay, fine. So what is our objective now? So now you have to start thinking about objective. And objective in this case is to reduce mass, right? Okay. So if now think about an equation that has the area in it for mass.
Volume?
Yes. So mass is what? Density times volume. And volume is what? Area times length. So you have to have both the constraint and the free variable. So now if I write that, then that's how I'm going to write it, right? So mass is volume, which is area into length into density. So now I've got two equations, one for my constraint, one for my objective. Both of them have one constraint variable and one free variable. So basically what I can do is I can rewrite this equation in such a way that to eliminate basically my free variable, right? Because that will change the design choice. So I'll rewrite this and I can basically just simply say that my mass, if I write it as, area is F over sigma yield, will become F into L, which are the constraint variables, into density over sigma yield. Are you with me? Right? So now what this equation is telling you, if you want to have a lower mass, what do you need to do? Because obviously this force you have no control over it. This is coming from the design requirement of, how much lift is required, right? So that force is fixed from your point of view, the maximum value. The length is also fixed. So you can choose a material that has a lower value of sigma yield and high value of lower value of density and high value of sigma yield to minimize this overall function. So you are not looking at the property separately. You are looking at the overall function being minimized, right? So this is what is then material index. But most of the time, it's our choice as a designer that on the graph we want to use it in the maximize format or the minimize format. So I can rewrite this by simply reversing this equation. And I can say that my material index is sigma yield divided by density. And in that case, if I maximize this function, it will minimize the mass because it's been written in the inverse form, right? So now this is a simple example of a material index for a tie rod that is transmitting axial load and has a fixed length and has a known force F being applied on it, and it is objective is to reduce mass. Okay, we can repeat the same process for a different case, like in this case now it is bending. Okay, so bending of the beam, another very common function mechanically. And I'm saying we need a strong beam with given length. So length is again fixed, okay? Having section area as free variable. Again, I'm keeping my area as the free variable, okay? And the objective is to minimize mass. Again, right? Same objective. Only thing that I'm changing is the function, that from axial it has become a beam, okay? So again, I write down my objective equation, density into volume. This time I can also write my density as area into length, volume as area into length. So this will become density into area into length. Now for the beam, we have to now move from volume, just the area, to some other variable like thickness or width. Why is that? Because you see, the beam property changes depending on the moment of inertia. And that changes not with area only, but how the area is distributed. So for simple case, I'm saying let's now assume that this beam is rectangular. Okay, so I have made certain assumption. So the index that I'm going to derive will strictly speaking be applicable only on square beams. But we will use this index for other beams as well. And we just need to adjust the final answer with certain constants. But I'm not going to go into that discussion of those constants right now. But the main index will remain same. Okay, so let's now look into the cross-sectional area as this width t squared, right? Okay, so can I now write that the mass is density into t squared into length, right? Now, if where t is the thickness of the cross-section, the maximum stress in the beam under the influence of the bending moment m will be given by the functional equation now, and we'll say that the sigma is m over z, where z is the section's modulus, which is I over c, right? So section modulus, because if you can also write this equation as m into c over I, right? So that is the section modulus. Now this z, once you open up the value of I for a square beam and divide it with the c, which is half of the thickness, you end up with this equation bt squared over 6. Now what I have now is, if I put this back into my initial equation, because now which variable is free? It's the t variable which is free, isn't it? Because that is controlling the area. So I can basically put it back over here. So this becomes z is t cube over 6. I can now substitute it back into my stress equation, and you end up with stress is 6m over t cube. Okay. Now from here, I have now one equation of my free variable, other equation of my function. And both of them have the same free variable thickness. So I can again do the substitution. Like in the previous case, I substituted for area. I will now substitute for thickness. There is, of course, a little bit more calculation involved, because now it's no longer a linear function. Rather, t cube is 6m over sigma. So t is 6m over sigma raised to power 1 by 3. You with me? Yeah? Now I substitute this back into the mass equation. So now my mass is what? Density into 6m over sigma raised to power 1 by 3 whole squared into L. I now separate the constraint variables and the material property free variables essentially, right? Because material we are still free to choose. Constraints, so we are only left with constraint variables which are moment and length, and the material properties which are density and sigma yield, right? Now you can replace this sigma yield by sigma flexural if you want to be more precise, but sigma yield can also be used in this case. So now you see your material index that you minimize to minimize mass is now density divided by sigma yield raised to power 2 by 3. And if you write it in a maximization format, it will be sigma raised to power 2 3 over density. So with that, I come to an end of the main lecture session. I have left you with this demo, and I yesterday recorded this video, which you can play by either clicking here, or you can directly go on to the next slide and play it directly. So I have uploaded it on the my YouTube channel, so you can directly click on this and view this. Please make sure you view this before the next lab, so that you are familiar with how to then use CES to plot these indices. But that's only the start, because then we'll actually have some exercises to start selecting materials using this approach. Thank you very much.
Thank you, sir.